In this lecture, we're going to be talking about the public switch telephone network, or the PSTN, as well as digital networks that are offered by service providers such as wide area networks. We'll talk about the role of regulation in the history of the telephone, because that's important to understand how the government actually helped fair practices. And of course, even today, the role of government is important in ensuring continuation of fair practices as well as technical innovation. We'll talk about the PSTN, what it is, and then what the public digital network is, and in particular we'll concentrate on T-Carrier. Then we'll look at the wide area networks, other public service offerings, and the protocols or standards that we'll look at is frame relay, asynchronous transfer mode, and carrier Ethernet. And then finally we'll talk about how fiber optics has helped our digital networks in this form of standards such as SONET and the wide wavelength division multiplexing. So we'll first take a look at the history of the telephone company, because it shows a dramatic way that the government was involved in an enterprise that essentially was a utility as far as communications went. And so it all started in 1876 when Alexander Graham Bell demonstrates the viability of the telephone. And of course, he's not the only one that demonstrated the telephone. There was a gentleman named Elisha Gray who also invented the telephone. However, Bell reached the patent office just hours before Elisha Gray. And so if Elisha Gray had been a little bit faster, we might have been looking at a Gray telephone company as opposed to the Bell telephone company. So you have to think at the time that the telecommunications across the world was mostly telegraphs, and Western Union was the largest telegraph company in the country. And so Bell, not wanting to actually run a telephone company, decided that he was going to sell his patent to Western Union. And so he offered the patent for $100,000, but Western Union, after having taken a look at it, decided that it wasn't viable enough, that they didn't think that the telephone would ever be as reliable as the telegraphs that they produced on a daily basis. So this was seen by a lot in the industry, in hindsight, as one of the greatest missed opportunities in communications. So even though Western Union had rejected Alexander Graham Bell's offer, Bell knew how important a telephone was, because it would allow people to speak to one another real time without having to go through a telegraph office. And so in 1877, Bell decided to start the Bell Telephone Company. And of course, the telephone became very popular, and a lot of telephone networks started to sprout up in urban areas. And so it was so popular that, in fact, in 1885, AT&T was formed as a subsidiary of the now called American Bell Telephone Company. And AT&T's responsibility was to do long-distance phone calls, or to support long-distance phone calls between urban areas. Now, of course, eventually AT&T would become the parent organization to the local telephone companies. Now, Bell eventually left AT&T, but AT&T's popularity continued to grow. But eventually, Bell's patent expired, and so other telephone companies were able to actually start offering services in other urban areas. But of course, we know if you start a network within a stovepipe or just in a city, you're sure that it won't be interoperable with any other networks. And this was indeed the case, where long-distance calls between one city and another city were very difficult to do, if not impossible. So AT&T came up with this idea that, well, what if we bought up all the independent telephone companies so that we could push this whole idea of one system, one policy, universal service. So in 1908, this was the motto, and the whole idea behind the motto was that if you owned all of the independent telephone companies, then you can force standardization, and you can enforce some kind of quality of service to all your telephone customers. And so they proceeded to do this, buy up independent telephone companies. So AT&T started to buy up all these independent telephone companies, as well as they started to purchase majority share in Western Union, who they saw as the greatest competitor to their telecommunications or telephone business. And so the Wilson administration, based on the Sherman Antitrust Act started to look into the practices of AT&T. And so the Department of Justice began its investigation, and AT&T, of course, understood that this investigation was going on. So in 1913, the vice president of AT&T, a guy named Kingsbury, actually went over to the DOJ and said, well, instead of going through all this litigation, can't we just strike up some kind of deal? And so the DOJ said, yes, let's go ahead and do that. And the deal was that, number one, AT&T would stop buying independent companies around the country. Number two, they would relinquish their majority shares of Western Union. And in trade, the Wilson administration would start to regulate the services and the costs to customers of AT&T's services. And so this became known as a regulated monopoly free from competition. So essentially, the industry looked at it and said, okay, well, if you're AT&T, you're big enough, and you can be a monopoly as long as it's relegated without any fear of having any competition whatsoever. The job of regulating AT&T fell to the Interstate Commerce Commission, or ICC. And despite the agreement being in place, 223 of the 234 independent telephone companies were purchased by AT&T. So that's 223 out of 234. So obviously, the word had gotten out that AT&T was a regulated monopoly and did not have to compete fairly. Now, the Interstate Commerce Commission, or ICC, had many duties other than just monitoring AT&T. So in 1934, the Communications Act of 1934 created the Federal Communications Commission, and the FCC's responsibility was anything to do with national communications within the country. AT&T's strength just continued to grow as a powerhouse, and so finally, about 43 years later, one of the first successful challenges to AT&T's monopoly occurred with the 1956 Hushaphone case. And so Hushaphone was a small company that produced a small plastic fitting over the microphone of the telephone. Now, you have to remember that at the time you couldn't buy telephones from third parties. You couldn't even buy a telephone from AT&T. AT&T leased the telephone to you, and as a result, you would never be able to own it. They could do anything they wanted to with that telephone. So the Hushaphone, as this little plastic fitting over the microphone, was really helpful, especially in really busy offices where there was a lot of ambient noise, because what would happen is you'd be on a business call, and the ambient noise would enter the microphone, and it would make it very difficult to have a conversation. So by having the Hushaphone plastic, just a simple plastic thing that would sit on top of the microphone, you could actually reject a lot of that ambient noise. And so this was getting very popular because it's helping out. But AT&T saw this and they said, well, wait a minute, that telephone is ours and you can't place anything on our telephone. And so it went to court. First it went to FCC, and the FCC made the decision that, yes, it is AT&T property, so you can't do place, even if it's just mechanically, you could place a device onto that phone. Of course, it went up to the Court of Appeals, and then the court reversed that decision, kind of giving both FCC and AT&T a black eye, and said that if all it's going to be is a little plastic fitting that doesn't impact negatively the AT&T network, then there's no reason why they can't have it. So AT&T lost, Hushaphone won, and so that was the first challenge. So the next successful challenge to AT&T came in the 1968 Carterphone case. And so in 68, around the Texas and Oklahoma oil drilling areas, there was a lack of communication. There wasn't a really good way for drilling teams to contact either their field office or to headquarters. They had two-way radios, and so Carterphone came up with this idea that, well, we can connect your two-way radio to the AT&T network, and then you can call any telephone that's on the AT&T network. And so Carterphone's invention was very, very popular, but of course AT&T took a look at this and they said, well, if you're electrically connecting up to our network, you could damage our switches. And so they went up to the FCC, complained about the Carterphone, and so FCC took a look at this and they said, well, there's no reason why you can't do it. However, companies such as Carphone will have to abide by some kind of interface specification that AT&T would actually post or deliver. And so this was a big victory to anybody who wanted to connect up electrically to an AT&T network. So this was the second successful challenge. There were other challenges such as MCI. MCI had microwave telecommunications over long distances, and they said that they could compete for AT&T long distance routes if the government would allow them. And this was just one of many, many challenges to AT&T, and the government started to see that, well, AT&T, in keeping it a monopoly, wasn't being innovative. The telephone that was produced in 1877 essentially stayed the same all the way until 1982. And so in 1982, the D.C. Court of Appeals finally came up with the modified final judgment of 1982 that led to the divestiture of AT&T. In other words, the breakup of AT&T as a monopoly, so that the divestiture would happen 2 years later. So finally, the government and as well as consumers had enough of AT&T. The innovation just wasn't happening, and the monopoly wasn't serving a purpose. So the regulatory history of AT&T is pretty interesting, in the fact that, of course, it was built in 1877, and it was a technology that grew in popularity to the point where in 1908 they said, hey, in order to have some kind of standardization across the country, we have to buy up everything. It's got to be one company dictating the standards. And of course, today we don't do that. Today we have standardization organizations that help standardize a capability in the industry. However, we still have those enterprises out there that are going to try and put out their standards, as we can see with 3G and 4G and 5G cellular systems, that try and push out their standards first so that they, in fact, become the de facto standard and therefore gain the majority of the profits. So it's kind of an old story that still kind of exists. Another lesson that we've learned from this is the fact that if you have a telecommunications company that is free from any kind of competition, then innovation will be stagnated. And so we saw that with AT&T. We saw how it eventually led to the breakup of AT&T. So when divestiture took place in 1984, the existing 22 Bell operating companies, or what we just termed the 22 box, all under a single company, were broken into 7 regional Bell holding companies. And each one of these 7 companies would be independent companies, although if you would look at it, some would say that it still looks like a regional monopoly as opposed to a national monopoly. But that was the first breakup, a major victory for the consumer and for technology. So you might think, why did it take until 1982 for the telecommunications to really kind of open up as far as innovation and competition? And the bottom line was, in 82, a lot of new things, a lot of new capabilities were coming into the market. Not only personal computers, but we had the internet, and we had IC chips that were advancing in capability. So this was the right time to actually start breaking up any telecommunications company. And if you think of the other types of networks that were out there, the other one being the cable communications company. In 1984, they came up with the Cable Communications Policy Act to remove a lot of barriers for the cable companies and allow them to be, deregulated, essentially. And then finally, in 1996, we had the Telecommunications Act of 1996, which really led to a lot of competition, in which now cable companies can enter into the internet service providing telephone business. AT&T was allowed to actually enter into providing internet services for customers, and in trade, new entrants were allowed to use some of the local infrastructure of AT&T's to get to users within their networks for a reasonable cost. So this really kind of opened up a lot of capability, a lot of excitement, that innovation was just around the corner. And as a result, a lot of money started to pour into the telecommunications sector. And so that's why they called this the dot-com bubble, because obviously a lot of money came in, but that also leads to a lot of high speculation, overpriced market, and with not as equal results in the innovation department. And so as you would expect, because there was so much money and not enough product coming out, we had the dot-com bust, and a lot of new entrants had lost lots of money. They were actually no longer within the business. But one of the nice things about it is a lot of these new competitors, which we called CLECs, which are CLEC, which stands for Competitive Local Exchange Carriers, a lot of them, even though some of them didn't survive, they were able to lay a huge infrastructure, especially in fiber optic cables. And that fiber optic cables is essentially what we use today for our high-speed networks. So let's take a look at some of the components that makes up the PSTN, or Public Switch Telephone Network. Of course, we have our telephones that are going to be at the residence or at the business, and that's going to be connected up to a central office through a local loop line. Now, the local loop line is typically a dedicated line until a twisted pair, and the central office is actually the first switching facility that most phones will connect up to. In order to make a path through the network, you're going to use, however, other facilities that have what they call tandem switches. And so these switches that are here, we would call them tandem switches. You note in this diagram that you actually have two networks in the PSTN. One is the voice and data channels network, which has voice grade and data quality network, so it usually has fairly good bandwidth. And then you have the Common Channel Signaling Network, or CCS, which doesn't have to have as much bandwidth because it's only doing control and signaling. So you might be wondering, why do we need a Common Channel and Signaling Network? And so the simple answer is, so you can make a call at any time, so it's a kind of an on-demand service. Otherwise, if you didn't have a CCS type of signaling system, you would have to set up some kind of reservation for a circuit with the phone company and then with the person that you're trying to call. But we want on-demand service, and so that's what the CCS will give us. And so if you're at this phone here and you want to make a phone call to the other phone on the screen, then what you would do is you would pick up your phone, connect up to the central office, and the first thing you do is connect up to the CCS network. Now, the CCS network actually provides the dial tone. Once you decide to go ahead and make that call, you dial in the number, and that number goes through the CCS network, through the central office of the called phone, and then over to the phone. And you get one of two things. You'll either get, you'll hear the phone ringing on the distant end, or you'll get a busy tone. If it's a busy tone, then obviously you just hang up and then you wait for another time. However, if the distant end decides to pick up that phone, then a connection is made, and the CCS will give you a circuit through the more valuable voice and data channel network. So this is a good way to efficiently control the use of the voice and data control channel network, because you certainly don't want to do good bandwidth, good quality circuits for signaling when they can better be used for voice and data exchanges. During the duration of the call, the CCS will still monitor the quality of service of the call itself, and then when the call is ended, then it'll free up the actual circuit for other users to use. And then finally, when you hang up, then of course the link through the CCS is also released. Now, one of the things that you'll note is that because we're using a different and separate network from the voice and data network for our control and signaling, we call this out-of-band signaling and control. So that means that we're not using the voice and data channels for any kind of signaling purposes. Now, this is different than when we look at the local loop line, because if you look at the local loop line, we only have, until the twisted pair, one single local loop going from your phone to the central office. So as a result, you have to, on this single line, have both control and signaling as well as the exchange of your voice and data. And so we call this in-band signaling and control. So in other words, at the local loop lines, you're actually using the same band, same medium for both voice and signaling and control. So let's take a look at some terminology that's associated with the PSTN. And so here we see two LADAs, and so a LADA is essentially a local access and transport area. So you have a LADA here, and a LATA here. So two different LATAs. You could say that they're roughly comparable to a area code, as an example. And these LATAs will be controlled by a LEC, and a LEC stands for the local exchange carrier. So a LEC would be, say, for instance, Verizon, and Verizon would be controlling a LATA, and that LATA would be like an area code. And so we have two of these LATAs associated here. So, as an example, we only see the actual voice and data network. We're not showing the control and signaling network. But as you know, we have our phone. We have a local loop line that's going to a central office. And so you've connected to a phone call, and you've gone through, and you're using a data, voice and data link or circuit. If you were to call another phone that's within the LATA or within the area code, it's called a intra-LATA call. However, let's say you wanted to call outside of the local area network. So let's say you're calling here and you want to call a phone that's in this other area code. So you would go to an interchange facility. So this is a switching facility between LATAs, and that would hook you up to the LATA that you're trying to get to, the area code that you're trying to get to, and then you would go through that LATA and then get connected to your phone. So this call is called an inter-LATA call. So you're going from outside your LATA to another LATA, therefore going through an IXC facility of switches, which is then called an inter-LATA call. Let's take another scenario where you want to call to an overseas location. And so this time you're going to call overseas, you're going to go through, but instead you're going to be hooked up to what they call an International Gateway Facility, or IGF, and then that will connect you to the proper country using the country code. There's literally billions of phones out there in the world, and so for us to actually get to the correct subscriber number in an efficient manner, we have to use a hierarchical telephone numbering plan, and that happens to be the ITU 164 International Telephone Numbering Plan, which is sponsored by the Numbering Plan Administration. And so this is a 15-digit maximum telephone number that has a country code, a national destination code, and then subscriber number. So national destination code within the country is going to be, like in the U.S., that would be our area code. And then, of course, within that area code, we would actually have a subscriber number. So that gets us quickly to the switches and the switching facility that we need. Because, as an example, if we were going to make an overseas call, it would send us directly to an IGF facility. If we know that we're going from one area code to another area code, it would directly switch us quickly over to the IXF, and so our IXC. And so this would be a more efficient way than if you can imagine having to go through a database of all of these numbers just to find the right call, considering there's billions of them, that it would take a very, very long time. So hierarchical numbers such as the MPA is just what we need for this. And you'll see that even in the internet, we use hierarchical IP addressing. Now let's talk about what the customer premises equipment is and what the DMARC is. So prior to divestiture in 1984, based on the MFJ of 1982, the telephone company actually owned your telephone and everything connected to it. So if you had a telephone, and this was your residence, and then you had your local loop going to the CO, then that telephone would be the responsibility of the telephone company. Of course, once divestiture happened, then we could buy our own phones, and of course, if we bought our own phones, AT&T would not want to be responsible for the upkeep of that phone. And so we would have this thing called a DMARC, and this DMARC would be where the responsibilities of the telephone company or the telephone network stopped, and where the responsibility to the homeowner or the customer began. And so it would be in this place, and typically what they had was this huge panel with a bunch of fuses here, so that if your house got a lightning strike, if you had an overload on one of your pieces of equipment, it would blow the fuse at the DMARC, and the network, the AT&T network, would be essentially unhurt. And so essentially, this right here would be your customer premises equipment, all the equipment that the CO would not be responsible for. So let's go ahead and clean up this drawing just a little bit. Okay, so let's say we are going to change this out and just have a DMARC here. And then we're going to just send this all to the service cloud. So this is going to be our service provider. And of course, this is going to be the CPE. And so traditionally, it's been pretty easy. We could just say that, well, I'm going to buy my telephone, I'm going to buy my own PC, and then maybe I have a fax machine or some other thing that I'm going to use, and I'm going to use service provider network to get into that. And so obviously, all of the equipment in the CPE would be my responsibility. But as services increased and different types of services came into the home, then you can see some service providers will actually support something like, as an example, a set-top box. You might have a set-top box that's going to give you all kinds of programming, say from Verizon Fios. And so if something happens to that set-top box, well, guess what? Verizon is going to be responsible for it, even though it sits on your side of the DMARC. Same thing as if you had a router so that you could set up your own network and you just happen to use Verizon, then that router most of the times would be the responsibility of Verizon. So, of course, they're leasing it out to you. That doesn't mean that you can't go out and buy your own set-top boxes or router. It'd be a little bit more difficult to do because you'd have to work with the service provider to get it all set up properly. And so what most people do is they'll just essentially lease the set-top box or router or any other devices so that they don't have to deal with it. And if there is a problem with it, it's going to be the responsibility of the service provider. So the whole idea of what a CPE is and the equipment that actually sits there is a little bit fuzzy, especially when you take into consideration what the DMARC is. However, the DMARC is still there, and the DMARC is still there to help protect the service provider network. And then there are still equipment that are considered to be your problem, not the problem of the network that you have to maintain. In this section, we talked about how regulation helps to shape the public communications networks, such as the PSTN. We also talked a little bit about the PSTN architecture, the difference between the voice and data network and the CCS or signaling network. And we talked about the differences between in-band and out-of-band control and signaling. We also talked about the hierarchical telephone numbering plan, and then definitions of LECs, LATA, what an intra-LATA call is, what an inter-LATA call is, and what IXC, IGFs, and the CPE and DMARCs are. In this final segment, we're going to be talking about the public data network, what T-carrier is, wide area networks, and some of the protocols such as frame relay, asynchronous transfer mode, and carrier Ethernet, and then we'll discuss SONET and wavelength division multiplexing. Initially, the PSTN was all analog. However, as more and more subscribers came onto the telephone network, it made a lot of sense to go towards the digitization of their trunk lines, because we know that digital communications is much more efficient than analog communications. So for a long time, the PSTN was involved in digitizing their network. However, it wasn't until computers became real popular, and especially research institutions with mainframes wanted to connect up to other institutions or other facilities and businesses, that the PSTN started to look at ways of offering digital communication or digital connectivity to these institutions. And so one of the first ones was called T-carrier. And so T-carrier was a leased line that universities or businesses would use to actually connect digital communications, whether they were digital networks to one another or mainframe computers. Now, a digital T-carrier was pretty popular around the world, and there's several different versions of the T-carrier. T-carrier is popular in the U.S., but then if you go to Europe and ITU countries, then you're talking about E-carrier. There's also a J-carrier that was popular in Japan. But they all have some commonality, and the commonality for the channelized version was that they were all based on the DS0. So let's talk about what the DS0 is. We mentioned this earlier, but a DS0 is essentially a digitized voice grade circuit that has not been compressed. And so we said that if we wanted a voice grade signal on an analog PSTN, we would need a bandwidth of at least 4,000 hertz. And so what we would do is we would send this through the PCM process here, and pulse code modulation meant that we were going to sample this at a Nyquist rate of greater than or equal to 8,000 samples per second. And of course, the quantization bit depth that we would use, or that the PSTN would use, would be 8 bits. So this would be 8 bits per sample. So if you want to know what kind of data rate you would be required to actually support this digitized voice grade channel, you would say that your data rate, and we'd just say the capacity needed to be 8,000 samples per second times 8 bits per sample. Of course, samples cancel out, leaving you with bits over second, which is 64,000 bits per second, or 64 kilobits per second. And so this rate is what we call a DS0. So the DS0 at 64 kilobits per second represents one voice grade call that's been digitized without compression. So as you can see here, that DSO lines up with one DS0 at 64 kilobits per second. If we looked at a T1, the T1 actually equals 24 DS0s, which is also called a DS1. And so this ends up being 1.544 megabits per second. And so the E1, the E carriers are slightly different, but they're still based on DS0s. So you can see that it lines up to supporting 32 DS0s at a rate of 2.048 megabits per second. So what we're going to concentrate on is the T1, which supports 24 DS0s at a rate of 1.544 megabits per second. And we'll show how we actually do that through the use of this T-carrier frame. So let's take a look at the case of a T1. And so we said for T1, we need to support 24 DS0s, voice grade digitized signals at a total rate of 1.544 megabits per second. So the key into supporting 24 DS0s comes in the T1 frame. And so this is a T1 frame. As you can see, there's only going to be one framing bit at the beginning, but then each of the DS0s up to 24 will be supported by only 8 bits for each DS0. 8 bits or 1 byte. So if we want to find out what the total bits per frame is, we'd simply say, well, we have one framing bit plus 8 bits times 24, and that'll give us 193 bits per frame. And if we have 193 bits per frame, then we know that we're going to have to somehow, because the DS0s are interlaced and only 8 bits are supported by every frame, we're going to have a frame rate of at least 8,000 frames per second in order to support 24 64 kilobit per second DS0s. And so we can see that if we have 193 bits per frame times 8,000 frames per second, we come up with the 1.544 megabits per second for the T1. So how does that work per DS0? Because we're interlacing that data. So let's just take a look at DS0, 3. So this is the third DS0 supported by the T1. And we're going to say that, well, every frame is only going to support 8 bits. So this is 8 bits per single frame. However, we know we're going to have a frame rate of 8,000 frames per second. Frames cancel out, just leaving us with bits per second. And of course, this is equal to 64,000 bits per second, or 64 kilobits per second. So this is how we actually support 24 DS0s in a channelized version of T1. Now there's also an option to go with an unchannelized version, which means that we don't have this particular frame setup. In other words, we can use the 1.544 megabit capacity of the T1 any way we want to partition it, any way we want, or just use the entire bandwidth of the T1 for a single channel. So that's the difference between channelized and unchannelized. So keep in mind that T-Carrier is essentially a dedicated leased line. So if you're a research institute and you want to connect your mainframe up to another research institute's mainframe, having a T-Carrier in the middle is probably good, because you're going to have it 24/7. No one else will be interrupting you, and even though it's maybe bursty data and you don't use it all the time, you're going to be paying for it all the time. And so let's say another research institute says, hey, I'd like to be part of that network. They come online. Well, you're going to have to purchase another T1 carrier, and so that now you've doubled the cost of your dedicated lease line. So as you can see, it's not very extensible when it comes to expanding your network, your digital network. And we'll talk about the wide area network and how that was able to create a lot of cost savings for especially this type of scenario. Let's talk about another topic, switched virtual circuits and permanent virtual circuits. So let's talk about public data network. And of course, a public data network is a digital network, usually provided by the same service providers that gave us the PSTN. And so it's a PDN that's going to support wide area networks, which are going to help alleviate some of the issues that we find with the non-extensibility of our T1 local lease line or lease lines. So let's talk about, if we had a digital network, what the difference between a permanent virtual circuit is and then a switched virtual circuit. Let's use this very simple digital network to demonstrate PVC and SVC. And of course, when we're a virtual network, then we can actually have all of the channels, all the medium shared by more than a single call or single node or user. And so everything is separated by either time slots or packets. And so in this case, let's say looking at the top network, we're going to have a call between A, and let me get my pin here, between A and H, and then simultaneously a call between B and G. So let's take a look at, see what that would look like. So A would make the call, and A's call would of course just be sharing time slots on the physical medium till it reaches H. And then simultaneously we get a call that's going to be sent out by B. And so once again we're going to share the link between C and F virtually until the call gets up to G. And we could have many more users on that same link. So now we have a virtual link. So now let's take a look at PVC and SVC and how those work. So we'll look at the left one and we'll say that these two represent PVC. And this will be the first call, and then this will be the second call. And this is going to be between A and H, A and H. So this is a call between A to H. So for some reason, maybe it's because of propagation delay or whatever, we want to have a permanent virtual circuit, which means that we want our circuit to always run through A to C to F to H, no matter how many times we call. Now we know that because we're virtual, other users may use those links as well, but we want to make sure that our routing is always the same. So if we call for the first call, and so let's go and take a highlighter. So the first call is going to go A to C to F to H. And then we hang up, and then we call for the second time, but because we wanted to have the permanent virtual network, we will have the exact same path, and therefore the same propagation delays through that same path. Now, another way we could treat a PVC is that we want to be on 24/7, and so we want to treat this as a dedicated, similar to a dedicated line. So we'll just say that it's kind of like a dedicated line, and let me get the right color here. So we want this dedicated on a 24/7 basis. So we can do that as well. We can say PVC, we're going to treat it like a dedicated lease line, like we did with like a T1 as an example. But in this case, it's virtual because we know that we're going to be sharing some of the links, some of the channels with other users. So we'll do the switch virtual circuit on the right side here. And when we think of switch virtual circuit, it's got the same concept as circuit switching on a telephone, in that you can make several calls, but you're not guaranteed the same path each time. So once again, we'll say that we want to do a call from A to H, and then we're going to have two attempts, the first attempt and then the second attempt. And so let's take a look at the first attempt, and once again, we are going to be sharing all the links. So we're going to just have time slots that are going to establish a call between A to H. Then we stop, and then we make a second call, but we're not going to be guaranteed the same path. So this time we may be given something that looks kind of like this. So that's the difference between PVC and SVC. With the popularity of the local area networks, service providers began to give wide area network services to their customers. So obviously, if you had a local area network and you wanted to connect up to several different local area networks within your organization across the country or even across the world, you'd be hard-pressed to buy local lease lines or dedicated lease lines for every single connection. And so therefore, the service providers realized that there was an opportunity here to provide a layer 1, layer 2 wide area network that would actually connect not only just the local area networks together for an organization, but then also mainframe computers. So when we talk about wide area networks, we're still talking about a layer 1 and a layer 2, layer 1 and layer 2 protocol. So keep in mind that the wide area network is a data link layer network, which means that the entire network is going to be owned and operated by either a single organization or, say, a service provider. And as such, unlike the network layer or the what we know as the internet, we don't have end-to-end connectivity. Now, that doesn't mean that you can't have end-to-end connectivity, but you would have to interface several wide area networks, several service providers together to get that. And so one of the first ones one of the first standards that was out, that was published, was frame relay. And frame relay was considered a fast packet technology. And typically when you talk about fast packet technologies in the day, you're talking about something that's 100 megabits per second, pretty slow in today's world, but that was considered pretty fast. It is packet, but packet in the sense that's variable size frames. So it's not what we think of the traditional datagram or packet switched networking that is really kind of IP and at the network layer. It does describe both layer 1 and layers 2. It's connection oriented within the wide area network. So if you had two different wide area networks that were going to interface, then it's not so much connected oriented, but it is definitely connected oriented if you're talking to two nodes within the same wide area network. Now, frame relay was really kind of one that was based for use with bursty networks. And so these were like local area networks or mainframe computers where the actual amount of data would be in a bursty nature. It wasn't like real time, wasn't like voice type of information or signals coming across. And so that was okay to use the variable size packets. But of course, if you're going to be talking about doing voice or real-time communications, you need to have some predictability in your propagation delays. And you're not going to get that if the sizes of your packets vary depending on who's using the network at the time. So frame relay wasn't really good for voice. They did have a VoIP over IP, a voice over IP use over frame relay. However, that was kind of an exception that they had to put into the standard a little bit later. But the traditional frame relay could not really support any kind of voice or real time. As it became more popular for digital networks to support real-time data exchanges such as voice and video, there needed to be a way to actually do that over a wide area network in support of both local area networks and computers. So asynchronous transfer mode was specifically designed to not only do data, but then to also do real-time voice and video. And so it also was a fast packet technology. And with the ATM network, you could also have connection orientation. And then the way that it was able to support the real-time voice and video was through cell switching. And with cell switching, each one of the cells that were transmitted, instead of packets as an example, were 53 bytes long. And so it didn't matter how much information you had to send, it would always be 53 byte cells that would be transferred. And as a result, because of the standard size of the cells, you could be able to switch and determine with pretty good certainty what the propagation delay and the processing delay would be. So in that case, you were able to support real-time communications. And also because of the fact that you had a better handle on propagation delays, you were able to also provide a quality of service guarantee. So you can see in Figure 9.9, this is a generic representation of an ATM network and how you have interfaces between private ATM networks as well as public ATM networks. And so you would have a local area network, and through a private UNI, which stands for User Network Interface, you would enter, as an example, if you had a private ATM network, the private ATM cloud. And so the private ATM cloud would consist of certain cell switches that were connected to one another through network-to-network interfaces, NNI. And if you had to connect to a public ATM network, say a public ATM network run by a service provider, you would go through a public UNI or a public user network interface to go into the public ATM network through their network, cell network. And then if you wanted to reach a local area network 2 that's on a private, that's on a public ATM network, then you would just go through the public user network interface to LAN 2. Now, this is a very generic picture, and it's the same kind of picture that you would expect to see with a frame relay network. The only thing would be you change out the ATM switches for frame relay switches. So one last note about ATM is that ATM was usually used with a layer 1 standard called SONET. And SONET stands for the synchronous optical network, which we'll talk about in the next couple slides. But it's a optical network based on fiber optic cables. And so this provided a high-speed physical network in which ATM could be placed above. Finally, we'll talk about carrier Ethernet. And carrier Ethernet is really the standard of choice now, because ATM and frame relay, they still may exist out there. Networks may exist, but they're not used as much. Carrier Ethernet is obviously the one that's most desired as far as interconnecting Ethernet local area networks. And for the reasons that should be obvious is that if you're going to use a carrier Ethernet to connect up to several local area Ethernet local area networks, then that makes a smooth native transition. Even though, like I had mentioned before, we have to be careful because when we talk Ethernet, we're really talking about a lot of different specifications under that particular standard. Now, carrier Ethernet is only possible because of the fact that we can avoid collisions if we're using switches and full duplex connections. And so if you have that and you can eliminate the data collisions, then you can extend your Ethernet in this case, metropolitan area network, to a much farther distance and support a lot more computers. And so that's the reason why Ethernet is popular today. You don't have to change from native Ethernet. It's a Ethernet, something that's familiar to most people. It's easy to implement. So while carrier Ethernet became very popular, especially with service providers who wanted to provide this service, it became pretty obvious that because of the many parameters that go into an Ethernet local area network or even a carrier Ethernet network, that there needed to be some kind of standardization as to the knowledge required, the certification of equipment, and then the certification for services for a service provider. And so the Metropolitan Ethernet Forum essentially made up of service providers and manufacturers, got together in 2001, and they created a certification process. And the certification process was one in which if you wanted to really truly have interoperability, you had to have certain certifications, and those certifications would be in the areas of services, manufacturing, and then professional competencies. And so that really brought the entire Metropolitan Ethernet service providers, manufacturers onto a single page so that they could actually build interoperable carrier Ethernet capability. And so you can see in this diagram that if you had one Metropolitan Ethernet network and two, and maybe they're controlled by different entities, that with the certification process, you would know that you would be able to interface with that other Metropolitan Ethernet network without too much problem. And the same would hold true for subscribers or to go into even non-Ethernet networks. So the Metropolitan Ethernet Forum offered several certifications that you could go for if you were an Ethernet service provider. And so one was called the E-line service. Is a pretty basic service where if you had your Metropolitan Ethernet network, you could connect two user interfaces, network interfaces together. So in other words, you could have two LANs connected to one another. You could also have an E-LAN service where you might have more than one local area network or more than two local area networks that you wanted to connect up to. So the E-LAN service would connect several into a single Metropolitan Ethernet network. And then, of course, you'd even have an E-tree service where you could have a hierarchical model in which each of the local area networks was going to be connected directly to a main root Ethernet local area network. So this would provide a lot more control if you were in like a headquarters to field office setting. So the first three models we looked at if you were within the same Ethernet network. But if you're going to talk to or connect up to another carrier Ethernet service provider, then you really need to get your act together. You really need to understand the interface. And so E-Access was one of those services that MEF looked at, where if you have a local area network in one carrier Ethernet network and wanted to connect up to a second one that happened to be located on a separate carrier Ethernet network, then you'd have to have some way of connecting the two service provider networks through some kind of network-to-network interface. And so doing this would allow you even greater distances to connect up to LANs that may be like across the globe or across the country. And then the last service is the E-Transit service, and this one kind of extends it even more. What if you didn't have your first two Metropolitan Ethernet networks, maybe they weren't connected. Maybe you had to go through some intermediate network, and one in which you don't have an end local area network attached to it. And so this is what the transit service is, in that you have a local area network connected up to MEN1, and then one connected it up to MEN2, but there's no local area network connected up to this intermediate LAN. However, in order to connect the two LANs together, you had to go through this intermediate carrier Ethernet network. And so this would be essentially the E-Transit, transiting through a third-party network to actually get to your destination. Next, we'll talk about the use of fiber optic cables in Layer 1. And if you recall, when I talked about ATM, I said that ATM was usually paired with a Layer 1 SONET using fiber optic cables. So what is SONET and SDH? Well, SONET is the synchronous optical network, and its counterpart in the ITU is SDH, which is the synchronous digital hierarchy. So their relationship is very similar to the T carrier and the E carrier in that they are both based on how many DS0s they'll support. The other thing about SONET is the fact that it's a synchronous network. So that means you not only have the network where the data is going to be switched and moved, but you're also going to have a timing network. And this timing network will ensure that good timing gets to every single SONET node. And as such, it can support very, very high data rates. Now, one thing about the SONET SGH network is that because of the synchronous timing and because of the fact that if you wanted to increase the capacity of a switch, you had to change out a lot of equipment. So the equipment and the changes would be very expensive, and so therefore the SONET SGH networks were not very extensible for those reasons. One of the other things that we have to take a look at is the fact that when we're talking about SONET, we have to take electrical signals, convert them into optical, and then back. And so as such, when we take a look at the optical and electrical side, we need to be able to also characterize them in bit rates. And so we have this in this table here, the optical bit rates. And so you can see that there's like an OC1 optical carrier to 3 all the way out to 3072. Now that's the optical, but when you talk about the electrical signal bit rate, then with SONET, we call it an STS. And so the STS, we have an STS 1, 3, and so forth. And so each one of those are going to, like for instance, the OC1, which equals the same rate as the STS1, will support 627 DS0s and have a total bit rate of 51.84 megabits per second. When we go and take a look at SDH, however, SDH still calls their optical side OC, or optical carrier, but on their electrical side, they change to STM. And it's slightly off as far as the mapping between all of the OC, SONET, and SDH. As you can see here, that if we see that an OC3 will equal an STS3, but however, this only equals an STS1. And at that STS1, it has a maximum bit rate of 155.52 megabits per second and will support 1344 DS0s. And so you can see all along this entire table the differences between all of those different rates. Now, even though SDH and SONET may have different nomenclature as far as STS or STM, the bottom line is they are still made up of DS0s, and so as a result, conversion from one to the other isn't as difficult as it might seem. So the popularity of SONET was quickly overtaken by wavelength division multiplexing for several reasons. Number one, it was actually simple to add more capacity. All you would have to do is add an additional wavelength card into the multiplexer, and you didn't have to worry about all the timing because it was not synchronous timing networks, and so it made it much easier. And so a lot of organizations started to, and service providers started to move towards WDM. Plus the flexibility of WDM. With WDM, you could definitely put a SONET. So if you still liked SONET and you wanted the SONET network, one of the wavelengths of light going in WDM could be SONET. It could also support just plain ATM if that's what you wished it to do, as well as other things like carrier Ethernet or maybe even IP in some circumstances where maybe you didn't need a day-link layer. It's just a layer 3 directly over the physical layer. So there's a lot of flexibility with WDM, and it's something that's covered with ITU optical transmission bandwidth windows that are essentially published for each of the windows so that we have some commonality globally for the type of signal that's coming in optically. Now, of course, the WDM did not do any kind of transition to an electrical signal. That would have to be done by the end equipment, but at the same time, it was very simple and very easy to implement. So in this section, we covered the T carrier, we talked about the T1 frame, and the difference between channelized and unchannelized T carrier. And then we talked about PCM and DS0s and how important they are with T carrier, as well as the DSO's importance in SONET. Then we talked about some wide area networks, such as frame relay, asynchronous transfer mode, and then carrier Ethernet. Then we went down to the physical layer. We talked about some fiber optic standards, such as SONET SDH, and how we labeled our optical signals and our electrical signals. And then finally, we discussed wavelength division multiplexing.